how they relate to each other, right? Yeah. When you study a system, you have input, you have an output, you want to know how they relate, right? Okay, so what is the parameters? Okay, so later we'll see. Okay, so that's why we want to see whether the two process, okay, whether they are independent, whether they are correlated or not. Okay, so two random processes x and t are independent. Okay, these two are independent if for all value of t1, t2. Okay, the two random variables are independent. So if we prove that xt1 and yt2 are independent, then xt and yt are independent. So again, this is how we test whether two random processes are independent or not. Okay, yeah. So same concept. If xt1 and yt2 are uncorrelated, then xt, yt are uncorrelated. Okay, yeah. So, yeah. For all value of t1, t2, that means include t1 equal to t2. Okay, so for all value of t1 and t2, that include t1 equal to t2. Okay, so if at all value of t, x and y, they are uncorrelated, then x, y are uncorrelated. Okay, so this is how we prove. So again, similar to random process, if they are independent, then it's uncorrelated. But uncorrelated doesn't necessarily mean that the two random processes are independent. So same as random variables. Okay, if independence definitely is uncorrelated. Uncorrelated doesn't mean that they are always independent. This is especially when your means, okay, when the means value somehow happen to be 0. Okay, so 0 multiplied 0, you get 0, right? Yeah, but not necessarily is independence. Okay, just happen that the expected value is 0. Okay, so that is the easiest way to remember. Okay, yeah. Except for the Gaussian process. Okay, so remember when we have a jointly Gaussian process, so independence and uncorrelations are the same. Okay, only for Gaussian process. Okay, so that's why here we introduce cross correlations. Okay, cross correlations between two random processes x and y. Okay, so when you look at these cross correlation functions, look carefully. It's a cross correlation between x and y. Okay, between x and y, and they take different value of t1, t2. Okay, so again, t1 is for x, t2 is for y. So that's why we are finding the expected value of xt1, yt2. Okay, so what you need to calculate this? What you need to calculate this? You need to join PDF of x and y, right? Okay, you need to join PDF of x and y. Okay, yeah. So yeah. So another definitions: two random processes x and y are jointly y-sense stationary, or we can simply say they are jointly stationary if both x and t are individually stationary. So x must be stationary, y must be stationary, and the cross correlation function, this function, depends only on the difference. Again, it's quite similar definitions. It doesn't depend on the value of t1 and t2. It only depends on the difference between t1 and t2. That means the interval. Okay. If these are the same, then it's what we call a joint stationary. Okay, or jointly y-sense stationary. Okay. So yeah, not complicated, but when you look at the step by step and use the correct equations, it's supposed to be fine. Okay, we look at this. So I didn't give. Okay, so yeah, it's supposed to be some example that you have to do integrations. I remove those. Okay, you can refer to the textbook for some examples, for some exercise, if you want to practice integrations. Okay, so assume that two random process xt xt and yt are joint stationary. Determine the autocorrelation functions of the process. Okay, zt equal to xt plus yt. Or we determine the autocorrelation functions in this case. So that's why we want to determine the autocorrelation function of xt. So t plus tau t. Sometimes it's use t plus tau and t. Sometimes it's just use t1 and t2. They are the same. Okay? Yeah. Sometimes they use t1 and t2. Sometimes they just use t plus tau and t. They are very much the same. Okay? So in this case, it's an autocorrelation function. So it's just x sec. So sec 1 of t1 is t plus tau. T2 is just t. Okay? So you just substitute here. And sec is equal to x plus y. So x plus y, x plus y. If you expand this one, okay? I believe you can do, right? Okay? You can just multiply them. So that is how you get x t plus tau x t, right? Yeah. If you expand it, so and then xt y t plus tau plus x t plus tau yt plus yt y plus tau. Okay. So that's why 1, 2, 3, 4. So this is autocorrelation function of x. This is autocorrelation function of y. This is cross correlation of xy. Okay? Yeah. Okay, so this is this is the first part. This is the last part. Okay, so this is the ry. So yeah, for this, okay, I cannot go there. Okay, so they are both rxy, but look at the the t and t plus tau, so that you get tau and negative tau here. Okay. So you can see the second term and the second terms and the third terms, they are not the same, right? The t are different. Okay? You can make them the same. Okay? Yeah. Then you add minus tau there. So that's why here is minus tau. Okay? Yeah. Okay, right? Because yeah. This one, yeah, you can change x t plus y t minus tau. Okay, so that's why the tau are different. You just minus tau to the first term and then you minus tau to the second term. Okay, yeah, it doesn't matter. Okay. Okay, so basically, I have covered all the basics for random variables and random processes. Okay, so those are the basics. Okay. So yeah, the last sections here. Okay, yeah, good news, it's not your test. Okay, but we will use this part. Basically, we will use this part in the later chapters. Okay, because this is where we put a random process into a system. Okay, so that's why you don't see this in the test. You will see this later in different chapter. You will still see this in your final exam. Okay, because definitely when we study a communication system, we are talking about when you have a random process, you go to a channels and what happens. That's what we are going to study in the next few chapter. So yeah, so that's why this part is important. Okay, as a foundation. So yeah, And we always deal with LTI, so we always deal with LTI, linear times invariant system. Okay, it's not the first time you see this system, right? Yeah, you have covered this in signal and system. Okay, so very good. Okay, so yeah, so the output is also a random process. So the output is also a random process, and it's definitely defined over the same probability space. Okay, so yeah, you just, again, I think it's easy. You imagine in our communication system, the input, the signal that you send, and the output, the signal that you receive, they must be in the same signal sample space, right? They must be all related. If you are sending 1 0, you will receive 1 0. Okay, you will not receive something else. Okay, yeah. So, okay, but there are some randomness in the process. Okay. So yeah, so, and also very often, okay, when we do modeling, our input we try to model as a stationary process. Okay, so that's why, let's say if you assume the input is a stationary process, okay, and of course we want the output to be stationary as well, right? Why? Again, when you design a model, you want the model to be able to use at different time. Okay? So your input is stationary, you want the output to be stationary. Okay? It's still a random process. Okay? But the statistical parameters should not change with time. Okay? Yeah. So that's fine. But it's not always the situations. Okay? It's not always the situation because the channel is random. Okay? That's the system that you pass through is random. So that's why we must find what conditions, okay, what conditions that the output process is still stationary. Okay, so all those we call that a random process. But this random process is more predictable than completely random process. Okay, at least that it's a random process. But for example, we know that the average is 0, and it follows the normal distributions. Am I right? So it's random, but we kind of like know this random process, similar to the output. Okay, we want that. Okay, yeah. Make sense or not? Yeah. So for the guys in future will know. Okay, your wife is a random process, but somehow it's more predictable. You know how to trigger her in the future, right? Same as your girlfriend, right? Yeah, it's random enough? No girlfriend. Okay. Later, no brush, okay? Yeah, later. Okay, so same, and yeah, under what condition, we also want to determine under what condition the input-output process can be jointly stationary, okay? Yeah. And yeah, how can we obtain the mean and the autocorrelation of the output process if you know only the input process? Again, this is something that's very important. Okay, yeah, you know the input. Okay, you know the input. Basically, input is something that you know. Okay, yeah, how do you obtain the statistical parameter of the output if you know the input and if you know the channels? Okay, yeah, and we know that we can, right? Yeah. So far, I hope that go through 3 weeks of lecture. Okay. Yeah, 2 weeks on random process. You can see we always have x plus y and so on. Okay. And z equal to x plus y. If we know x, if we know y, we know z. Right? Okay. Yeah. It's very much the same things. Okay. Yeah. So and also yeah, how do we obtain the cross correlation of the input and output? And this one definitely makes sense. Okay, we want to see how the output correlated with the input. Okay, yeah. So yeah, so look at here. Okay, if a stationary process, they have a means. Okay, we can say this x is input. Okay, so we know the mean is fx, and then we know the autocorrelation functions rx. Okay. So if this process pass through a LTI linear time invariant system, okay, and for this linear time invariant system, Okay, so the characteristic or the transfer functions, we can use an impulse response to represent the LTI system or the LTI filter. Okay, it's just an impulse response, impulse functions. Okay, so then let's say the output is yt. Okay, the output is yt. So xt and yt, that means the input and the output are jointly stationary. Okay, and then they have these parameters. Okay, and again, we will not prove every of this because that involve integration of the convolutions. Okay, so or maybe you have studied this in signal and system. Okay, so if you want to prove, refer to textbook. So these are the equations. How you calculate my from mx, ry from rx. Okay, and this is the cross correlations between x and y. Okay, so we just use it. Okay, we just use it. Okay, examples. Assume a stationary process pass through a differentiator. So in this case, in communication system, have you studied differentiator in electronic circuit? Electronic circuit, EC. You have done EC1 and EC2 already, right? So you're expert in IC design already, right? So that's why I believe you know the differentiator and the filter, very tough filter, amplifier, and so on, right? Okay, you're expert. So, yeah. I don't do IC design, okay? So we just study the system, the signals. So, let's say you have a differentiator, so the impulse function as the impulse function. The transfer function will be equal to this one. Okay? So you want to calculate, okay? You want to calculate the output, okay? The means and the autocorrelation functions of the output. So again, we just use these equations. So the means my equal to mx, ht, so the differentiation dt. Okay? So how do we get this equal to 0? Okay? So if you brought these differentiator functions, okay, it's an odd functions. Odd functions mean? Odd function means even functions, they are symmetrical at y, right? Odd functions symmetrical at origin. Am I right? So that's why when you integrate the positive part and you integrate the negative part, integration is the area under the graph, right? If you integrate, it will become 0. So that's why this part you get 0. So that's why the means of the output functions, regardless what is the means of the input function, output function, regardless the means of the output function and the input functions is always equal to 0. Okay? When you pass through a random process with a differentiator. Okay? Yeah. Okay. Second part. We calculate the autocorrelation. This cross correlation. Sorry, autocorrelation is this. Okay. So the autocorrelation functions. Okay. This equation. Okay, later. Okay, so we follow step. There must be a reason why we follow step. Okay, so we calculate the cross correlations using these equations. Rx multiply this convolutions with the impulse functions, not the differentiator, and then what happens here? So again, this is an odd functions, right? Odd functions. Okay. So again, it's an odd functions. So you can see here. Let's say that, okay, this is odd functions. So this is negative tau. This is tau. They will have the same value but negative. So that's how this will become this one. Okay? Okay, yeah. And if you look at the tables, okay, for these convolutions, when you take a functions, you do convolution with the differentiator, what you get is the differentiation of the functions. Okay, so that's why it's called differentiator. Okay, so that's why in this case, the negative is from there. Okay, and then when you do convolution of this one with the differentiator, you get the differentiations of the Rx. Okay, that's how you get this. Yep.
Why the delta function is odd?
Why the delta function is odd?
Because the question given.
Yeah, because the question given. Okay, and not because the question given. Because the function is odd functions.
The delta function itself.
I ask you why the sinusoidal function is odd functions.
Or
why the sine function is odd function and the cos function is even functions? Is the functions. Okay? Yeah, it's the function. I forgot how the differentiator function look like. When you plot the function, you get odd function is odd functions.
Oh.
Yeah. Why sine function is odd functions and why cos function is even functions? When you plot, it's odd, right? Yeah. Okay. The function is odd functions. Okay. Yeah. I forgot how the differentiator functions look like. Okay. Yeah. Okay. It's the functions or research. Okay, if I can find that, I show you. Okay, so yeah, it's a functions. It's a specific function. So in this case, it's an odd functions. Okay, so yeah, and this one RYT. Okay, yeah. So you can see Ry tau, Ry is equal to Rx multiplied with this one, multiplied with this one. Okay, so you can see this is one differentiations. Okay, if you actually we have done this right just now. Okay, yeah. Now that you will get this. Okay, so yeah, the same these equations. So h is the differentiator functions. So you substitute the differentiator functions, and the negative is just negative, differentiation of tau. So every differentiator is one times differentiation, so that's why it's two times differentiations. Okay. Okay, so another examples. So yeah, we repeat the process, repeat the questions for what we call a quadrature filter. Okay, so yeah, this filter is defined as this. And yeah, if we take the Laplace transform of this one, this is the Laplace transform. And then the output of the filter is actually the Hilbert transform of the input. I think in chapter 1, I briefly introduced what is a Hilbert transform. Okay, I think in week number 1, I briefly go through what is a filter transform. What is a Hilbert transform? Okay, a Hilbert transform is just very simple. It's just we add a 90-degree phase, okay, or negative 90 degree to the phase. Okay, so this is Hilbert transform, very simple transform. Okay, and Hilbert transform, you're always in the same domain. Okay, so this is frequency domain. Sorry, this time domain, you are still in time domain. You don't go to a different domain. Okay, you are still in the same domain. So this is Hilbert transform. So that's why I tell you that, you know, if you pass a signal through a quadrature filter, okay, what you get is the Hilbert transform of the input. Okay, so this is given by the questions. So again, we do these calculations for my equal to mx. Okay, so and again, this is equal to 0 because these functions, in this case, they have given you the function. I believe you can plot these functions very easily, right? So this function is just 1 over t. 1 over t is what? Yeah, in this case, it's easier. So 1 over t. Like this, right? Right? Okay. No, sorry. Yeah, so you can see it's odd functions. So when you integrate the odd functions, you always get 0. Okay? Because integration is the area under the graph. So the area under the graph, one is positive, one is negative. That's how you get 0. Okay? Yeah. But how? Sometimes you cannot remember, you know. Yeah. If you cannot remember how, you do these integrations. Can you do these integrations? Yes, you can do these integrations. Okay? Integrate of 1 over t is what? Ln, right? Yeah, and then you can do this. Okay? Yeah. So ln infinity is what? So it's ln infinity minus ln negative infinity. Is that equal to 0? Yes, okay, good. Your friend verified that. Okay, yeah. So you see, he doesn't need a calculator. Yes. Okay, yeah. Yeah, look like my friend. Yeah. So it's very lucky you got a classmate like this, you know. Yeah. Okay. Okay. Next, Rs5. So it's Rs, and then you do convolution with negative tau. Okay. So t you replace with negative tau. Okay. Okay. How to do this? How to do this? How to do this? How you do convolutions if you have this in time domain? You know, right? If convolution in time domains, if you change to frequency domains, your Laplace transform, what will happen? it become multiply. Easier, right? Yeah, similarly, if you have convolution in frequency domain, when change to time domain, it become multiply. Yes? No? Yes or no? Okay, yes, yeah, your friend say yes, okay? So that's why, here you need to do a little bit of Laplace transform, multiply, and then inverse Laplace transform, you will get back this answer. Okay? So add on to your list to do revisions, Laplace transform. Okay? So same for this case. Okay, same for this case. Okay, so I think I will stop here, a bit tired. Okay, so yeah, we'll continue tomorrow. Okay.